Hello and welcome to this module, which is about how to schedule tasks, or ideas about how to schedule tasks. And this is in the context of task parallel programming models. Let's revisit task parallel programming models a little bit. In a task parallel programming model, the idea is to expose parallelism, to expose available concurrency, and then let the runtime system utilize that concurrency to execute the task on different worker threads. So the threads are in best case sort of invisible or implicit to the programmer, and not really explicitly used as they are in normal threading models. So in a task parallel program, there is a sequential thread that is starting the execution that generates tasks, and these tasks are available during execution, and created tasks, they are put in a ready queue, and then the workers can conceptually take tasks from this ready queue and execute them, and when they're completed, they go and get the next one, and new tasks that are executed here at the worker can also generate new tasks that are put in this worker queue. In the end, there is a task dependency graph that may look like this, or in another way, depending on the program available. The point here is that the programmer specifies task creation annotations and do not really deal with which task goes to which worker. That is done by a user-level runtime system. So the module today is about this scheduling part here, how we schedule the tasks on the worker threads. Again, recap a little bit difference between threads and tasks. Assume a threading model where you have, for instance, POSIX threads or P threads, and you have two threads, and you have one thread executing here, and you have another thread executing here, and you want to, these threads actually need to update or use the same variable. So you have one thread here updating variable x, and then you use this variable x here in the first thread. Besides issues like memory models, which is sort of difficult to deal with here, we also have to deal with data races. So if we want to avoid the data race here, we definitely need some kind of synchronization here, specifying that you can't actually use x here until the definition or x has been updated up here. So there is a need for synchronization here. In well-programmed task programs, this is not really necessary, because instead of sort of relying on synchronization based on the updating of a variable, you have a task that performs the update of the x. It's joined here by the sync, and since you have a causal relationship between the sync, that you have to wait for the previously spawned thread, you know that x is available here, and you don't need extra kind of synchronization primitives. So in theory, you really don't need more synchronization primitives than the spawn and the sync here, although this is just in theory. Going back to scheduling. So we differentiate between tasks and workers. So in a task parallel program, we typically have one worker thread per hardware context. This is typically a core or another kind of a hardware thread. In a multi-core processor, it's typically then one thread, one POSIX thread, one P thread, or Windows thread per core. If you have a hyper-threaded or simultaneous multi-threading processors, you might want to have one thread per hyperthread. Then the operating system has a task to schedule these worker threads onto the cores. So for all practical purposes, the worker threads can be considered as proxies for cores. Then there is a user level scheduler that schedules the task on top of the workers. So we have kind of two-level scheduling here. So the program, when you start a program, you typically ask for a particular number of threads to use. You hope that the operating system is not overcommitted, so that you have available cores for the number of threads you have asked for, and then the runtime system, the user level runtime system, is responsible for schedule your tasks onto those worker threads. All the worker threads, they share memory, and they synchronize using typical traditional methods like locks or compare and swap and so on. So the implementation of the task parallel programming is very much like threads level programming. And then threads only synchronize using the sync object or task wait or whatever you have in different programming models. Well, in theory at last. Okay, as soon as we have created a task, it can be scheduled for execution, assuming all data it needs is available at the time of the creation. And there are basically three alternatives for scheduling tasks. You can either have a centralized task queue, or you have decentralized task queues. And if you have a decentralized task queue, you can work with work dealing or work stealing. Let's see simple examples of how these look like. In a centralized task queue, the workers, denoted by the red circles here, they generate tasks to the queue and a centralized shared common queue, and they pull tasks from it when they need work to do. There is a very good benefit of this scheduling method. It has extremely good load balancing properties, because there's always, as long as there are tasks to execute here in the queue, the workers have work to do. However, the shared queue can easily become a bottleneck. So unless the work per task is very large, this centralized run queue is not a good model for scalable solutions. But this is about the implementation. This is nothing you would sort of deal with in the code. Another approach is to have decentralized queues. So have one queue per worker thread, and then when you generate a new queue, a new task, you typically generate it to your local queue. However, if your local queue happens to be full, like this one, you'll find another queue which hopefully is empty, and put the work in that one instead. So this will lead to load balancing, because if you have one worker which has too much to do, it will spread the work to the other ones. But it has a load balancing algorithm which actually steals time from the workers which have the most amount of work to do. So to alleviate that problem, work stealing is a more natural and better and more robust scheduling method. In work stealing, the task of getting work getting tasks to work on lies on the worker which has no work to perform, like this worker here. So when you have an empty local work queue, you go to another one and steals work from that one, and hopefully you'll steal from someone which has the most amount of work to steal from, and then you are set to go and you fill your local queue, and you can do you have work to do here. Most work stealing algorithms work with randomized work stealing. So the choice of which worker's queue to go and steal from is made by random. The reason for that is that hopefully most queues have work to steal, and to actually find the queue which has the most tasks to steal from takes a lot of time. So to do that, it's not a good option. So the major benefit from work stealing compared to work dealing is that in work stealing, it is the responsibility of the task or the worker which has nothing to do anyway to find work to do, instead of, as in work dealing, taking time from the overloaded worker to find someone who has not work to do and put the work there. The work dealing approach would take time away from precious time from executing tasks, while in work stealing, this worker thread would not have anything to do anyway. So this is a good option here. So again, to recap, work stealing, each processor has its own local pool of work. When all local work is completed, it steals work from another pool, in most cases chosen by random. A spawn places a task in the local pool. A sync would check the most recent tasks in the pool, and if you have unstolen tasks, you execute them. If you have stolen but not yet completed tasks, you wait for them. But if you have stolen and completed tasks, you have nothing to do. And this is sort of actually comes to the waiting problem. So when you have a sync and you find a task which is not stolen, then it's okay, just run it. But if it's stolen and completed, yeah, fine, you return. But if it's in progress, you have to wait. What to do if you while waiting then? Well, you can do nothing, which is a waste of time. You can have more workers than cores and hope that the operating system will schedule those worker threads onto cores when the core is waiting. Or you can steal some other work, which is what most work stealing algorithms actually do. You can actually steal while waiting, but you have to be careful what to steal so that you don't steal things that are that lead to sort of circular waiting here. Again, this is nothing that you as a programmer would sort of be concerned with. This is about the implementation of the task parallel library or the task parallel framework, like OpenMP tasks or Silk Plus and so on. So this concludes this module about scheduling very quickly. Go to the website and follow some instructions on how to do the quiz. Thank you.